three-dimensional elements. Okay, the first type is 4 nodes tetrahedral elements. So here 4 node, we are saying that it is a linear tetrahedral element. So basically you have I, J, K, L as you've seen here. Then we have these 8 nodes brick elements. So it's basically a so-called cube types of elements. We call it linear hexahedral elements. So you have a total of 8 nodes. I, J, K, L, M, N, O, P. Okay, so as you have seen. So of course, from linear, these two types, basically you will see these main two types, tetra or hexa, right? Linear. In linear, so of course we also have higher functions. Basically quadratics. So from 4 nodes, okay, if you are increasing the mid-side nodes, or you are including the mid-side nodes, then basically you become 10 node tetrahedral elements. Then it's what we call quadratic tetrahedrals. So the fourth one is, of course, is the quadratic hexahedral, or what we call the 20 nodes brick elements, or the cube elements. Okay. So this is what we have in three, mainly very commonly used in three-dimensional elements, and that you will see tetrahedral, hexahedral types of elements that you available for you to choose. All right. So you see that we have 4 nodes for tetrahedrals, linear tetrahedral, 8 nodes for hexahedral, 10 nodes for quadratic tetrahedral, then 20 nodes for quadratic hexahedral. So what it means here, if you have 4 nodes, then you have 4 shape functions, right? 8 nodes, then you have 8 shape functions. 10 nodes, you have 10 shape functions. 20 nodes, you have 20 shape functions, right? So under here, there is another slide that basically show you linear tetrahedral, quadratic pentahedral, hexahedral, or brick, okay, linear and quadratic. Then we have another one, is called pentahedral. So linear is 6 node and quadratic at 15 nodes. So not that common, but sometimes when it is these two are more dominant, but then if the case of you cannot what we call, in the case of when after it discretize, okay, some shape it cannot be discretized using this. So some of the program or some of the software will making use of this pentahedron to discretize your models. All right, so the properties we have linear element, quadratic elements, right? As we have mentioned, right? Here just now we are talking about the most common one is tetrahedral and hexahedral. So here, if you are saying that both of them you have linear and quadratics, okay, higher orders. Okay, linear element, as I mentioned just now, in two-dimensional, good for deformations. So when you have a global motion, global response need to be determined. But in the case of you are moving towards a localized problems, for example, stress, when you have concentrations of stress, then probably you need higher accuracies or higher orders. Here, quadratic element is more suitable. Right. So if it's possible, okay, is you have to play around with the independency Tesla. So if it's possible, then you will choose higher orders elements. So 10 nodes tetrahedral and 20 nodes brick elements for 3D stress analysis. So stress analysis, usually we go for quadratics. So avoid using linear, 4 nodes especially, okay, tetrahedron, because it will be not that accurate for stress analysis. For deformations, okay, or in vibrations itself later on, we are more toward its global movement, global motion, or global deformation. So here, yeah, linear is good, right? It is sufficient enough, right? So again, like we have done in two-dimensional, deriving or determining the shape function. So here, of course, we don't really go into deriving, but good to know. Okay, so you have 4 nodes, you have 4 shape functions. So in this case, your displacement field, you have U, V, and W representing the displacement in the x-axis, displacement in the y-axis, displacement in the z-axis. So for 4 nodes representing the displacement in the x, y, z-axis, then you have 4 shape functions to determine. So here we have a total of 4 times 3, 12 unknowns or coefficient here to determine C11 until C34. Then if we set, okay, for the first one, if we set U equals to UI, okay, when U equals to UI, my X equals to XI, Y equal to YI, Z equal to ZI, like what we have done previously in deriving the shape functions. So we need 4 unknowns, we need 4 conditions to actually find these 4 unknowns. So using this itself, we will find C11, C12, C13, and C14. So similarly with C21, C22, C23, C24, and C31, C32, C33, and C34. All right, so if you can satisfy the condition, then probably we have our displacement field in terms of its shape function is U equals to S1 UI, S2 UJ, S3 UK, and S4 UL. 4 nodes, 4 shape functions. So all the displacement field in the 3-dimensional directions, I mean basically principal directions, basically you are sharing the same shape function. So this is your shape functions. So here, previously in 2-dimensional, okay, if you still remember, and we have a triangular elements. So we have 1 over 2a. So that is area of your triangle. So now this is V itself is the volume of the so-called triangle element. Okay, so here is talking about tetrahedral. Okay, so that is basically how you got your shape functions, the 4 shape functions. So the 6V is basically you can find from the determinants of your determinant of this metric itself. Let me say get you the volumes, right? Then at the same time, if you want to find AI, AJ, AK, AL, then probably the determinants of this metric itself, you will get this AI. So basically, if you want to find AI, then the arrangement is XJ, YJ, ZJ, XK, YK, ZK, XL, YL, ZL, ignoring removing the XI, YI, ZI. So in the case of you want to find AJ, then probably you have a XK, YK, ZK, XL, YL, ZL, then you have XI, YI, ZI, ignoring or removing the J parts. So similarly with BI, CI, and DI. So if you are talking about BI where related to X field, okay, X directions, then we do not need to input the X part. So what we have again is replacing this with 1, okay, and finding the determinant of this, basically we get the BI. So if you are getting CI itself, then is Y related, so Y all replaced by 1, and getting the determinant of it. Z, then you replace by 1, get the determinant of it, right? So that basically gives us the shape functions. So of course, this shape function is not only limited to the displacement field. So if you are having a velocity in fluid mechanics, the temperature in the thermal analysis, so they are also sharing the same shape functions. So also SI, S1, S2, S3, S4 related to the nodal temperature of I, J, K, and L. Right? So this is like what I mentioned to you. I mean, AJ, if you want to find AJ, here ignoring the J parts, right? So we have start from XK, YK, ZK, XL, YL, ZL, XI, YI, ZI. So it have to follow the flow, okay? So the following of this is a linear hexahedral. So linear hexahedral, basically you have 8 nodes. So of course you have 8 shape functions. So here itself is your the first shape functions. this is the first shape functions, second, right? Then you have the third, fourth, fifth, sixth, seven, eight, right? All multiplied with 1/8. Right, so for displacement field at V or U, okay, U is x-axis, y-axis is V, then also the same shape function is used, is derived, and W or z-axis also the same. Okay, so again, how to derive it is basically again same with what we have derived in two-dimensional. So here we we don't really need to focus on the derivation anymore. So for three-dimensionals onwards, I mean two-dimensional, we still can making use of these shape functions to determine the shapes, the let's say temperature, displacement at that, also stresses at the areas of the point at not within the nodal temperature or nodal parameters or the variable itself. But in three-dimensional, it's yeah, I mean it's used usually for a more complex problem. So it's better. We know it's good to know the shape functions, the nodal, how many nodes they have, what types of element they have. But then the what we call the software itself will help us to solve all these problems. Right? So good to know, and we choose the correct so-called types of elements later on. So if you are having temperatures, same lah, or if you have a temperature over an element itself, you have a total of 8 shape function also. Okay, so the 10-node tetrahedral element, quadratic tetrahedral, so you have total of 10 shape functions, right? So that relate to the nodal your so-called displacement field. So here you have the first, sorry. So here you have this one, 1, 2, 3, 4. Then here you have 5 multiplied by 4, 6 multiplied by 4, 7, 8, 9, 10. So for V also the same, for W also the same, or different displacement field also giving the same shape function. So this S1, S2, S3, and S4 basically is the one that use the shape function that you use in a linear tetrahedral. Okay, so displacement field or even the temperature change, okay, in thermal analysis also making use of the same shape functions for these 10 nodes. Then finally, the 20 nodes quadratic hexahedral, then of course you have 20, total of 20 shape function that basically you have seen here. So this is the first one, second, third, fourth, fifth, sixth, seventh, eighth, then another mid-side nodes, right? Another mid-side node, another 8, and sorry, another 12, right? Another 12 for the mid-side nodes. So Q, R, S, T, U, V, W, X, Y, Z, A, B. Right? So that basically gives us total of 20 shape elements, shape functions, okay, for this quadratic hexahedral. Right. So if you are, that is for U displacement field, V and W also the same. Then if you are having the temperatures, also the same for thermal analysis. Right. So that is the type of elements that we have. Okay. So in terms of finite element modeling, so same lah in terms of 3D. So we are talking about the meshing discretizations, okay, what types of mesh that we have in ANSYS. Then here in three-dimensional analysis, so we also have to, like I mentioned to you, we have to model as close as its physical behavior. Then we are dealing with the supports, the boundary conditions supports the loads, and as well as if you are having a multi-component, then the contact is also important. So contact between the two components coming into play is also important. So that is things that we have to look into. So we want to say that these are all the factors that can affect our accuracies. Okay, first is the mesh. Second one is the boundary conditions, the support and load. And if you have a multi-component, then the contact itself will affect the accuracies. Or beside of this, of course, our materials we use will affect, and also our geometry. So if you are having a 1 meter length, then you put 10 meter, then basically the entire results that solved basically is totally different. So that is the effect of dimensions. So meshing discretization. So just to repeat back, okay, linear is good for deformation, quadratic is for stress indices, right? So we have to find a cut-off point or strike a balance between the computational cost and the accuracies that we have mentioned. Right? So mesh independency test is the very important in this case. So if you are purely if your work is purely on computational, so a lot of time you will be asked how to ensure that your computational analysis is accurate. So if your work doesn't really involving experimental validations, so it's purely computational, so you have to show that your work is accurate. Okay, so one of it is your discretization, your approximation is good. Okay, so the size element that you use is good. Like what I mentioned to you, using a larger mesh size compared to a smaller mesh size, it changed a lot. Then meaning that is not reliable yet, your result. So you have to go through that independence test. Then probably it will help you to at least even without the experimental validations of your work, of your model itself, the mesh independent test at least will tell some things. Okay, so meaning that it is approximate with a correct mesh size, with the correct assumptions on the boundary, the supports, and even the contact itself to represent the actual physical behavior of our actual system, something like that. Right. So one of it is the meshing, the test that you have to do. Right. So here also the same I mean, you have a global, you have a local, global setting, local settings in 3D. So if you are in 3D analysis, so under the workbench, the project schematic there, you have to choose that is 3D. Then only you can see the 3D types of elements. Later on, I will show you. Right. So here you have few types: automatic, tetrahedron, hex dominant, sweep, and multi-zone. Right. So you see that you have a hexahedron type, tetrahedron type, and this sweep and multi-zone basically is more towards something similar like automatics. Okay, that in sweep is for a sweepable body. So if your model is a piping that when you model, you are doing this sweeping along the line, let's say a curved line or what, you do a sweeping. Then in terms of discretization, they will also use the sweeping method to discretize into 3D elements. Right, so we will look into this. So automatic meshing method, if you select it, basically is start with sweep. Okay, any bodies that is sweepable, it will use the what we call sweep methods. Basically, it start with sweep method to discretize it. So sweep usually is hexahedron, right? Hex elements, okay? So it started with that. So otherwise, okay, if cannot sweep one, okay, cannot be swept one, then probably use this tetrahedron. So it's a combination. If you use automatic, basically it started with to find whether your body is sweepable or not is swept, then you use discretize using hex element hexa. Then if no, then you will use tetra. So tetrahedron is you have later on you have two settings. This is what we call patch conforming. So it's more towards bottom up. Later on we will look into it. Right. So tetrahedron. So the next is tetrahedron. So tetrahedron you will have is where the tetrahedral mesh is created. So mainly on using tetra mesh types. So under this tetra, you have two algorithms where you can choose how it is being discretized. So one is called patch conforming, like just now we have seen in automated one, when another one is called patch independence. So after the element, you have this element inside nodes, like I mentioned to you, either you want to use quadratics or you want to use linear. Okay, so under the new version, you will see the orders only of linear or quadratics, not drop and cap anymore. So if you are using tetra, so you have to choose whether you are using patch conforming or patch independence. So patch conforming is more towards a bottom up approach. So you start your mesh with from the edges, faces, then only body. So if you have a two close face, okay, in your entire body, 3D bodies, so it will start meshing at this particular so-called area or region first, then slowly go out to the entire bodies. So if you are very close itself, then this particular part will have it will use a more refined elements because it's close. So you have two, basically these two part is this part itself, this region itself is two faces, okay, two different faces. Then it detected, then it basically will go towards a final mesh, right? In this case. So if you are using patch independence, so if you in that case, so it doesn't really consider whether it's a two faces or not. So basically, it is more towards top-down approach. Okay, so the entire body will be discretized. Okay, even you have very too close, so it won't basically consider, it will still treat as one body. So it will discretize according to this particular body, unless you have to under this patch independence. Okay, in the case of you want this, you are saying that these are the two different bodies, two different phase, then you have to manually, okay, assign, okay, name it. If you without any name selection, so basically it will basically top down approach or discretize into what we call treat as a one body and discretize accordingly. So if you manually, okay, assign, okay, this is a phase one, this is phase two, I want it to be more details, okay, two face, okay, two faces, then the edges itself, it will be more refined. Then if you name it, then under here, it will basically do like what you see in patch conforming. So for example, here also the same, okay, if you have a curvature like this, fillets or whatever, okay, so it's a curve, then if you don't select it or name it, you want it to be more refined, okay, or even the setting that you set is below the requirement that you set, then it will be ignored and it will treat as one free surface. So in the case of you set, let's say 80 degrees, so if find out that is basically you have fulfilling these name features, then it will help you to refine at the edges here. So it's good. For example, you are looking into stress analysis where you have a stress concentration at this particular region, then probably you need a refined or what we call higher orders or refined mesh, okay, in these particular regions. Right? So that is patch independent. Next is hex dominance lah. If you are using hex dominance, so basically it's just like just now automated, it use sweep method, then it also is a swap. Using sweep method, then you are using hex also. So this hex dominant, basically you try to discretize using the hexahedron mesh. So it's usually for those body that cannot be swept and you still want to use a hexahedron, then basically use hex dominant. So what hex dominant compare to what we call? Of course, this hex dominance it will reduce compared to let's say tetra and hexa. So you see that in terms of discretization, it will basically reduce the element count. So you are using lesser elements compared to tet. Then of course, in terms of computation, it will be faster. Then the mesh, okay, of course, is dominated by hexa, but at some curvature or some parts that some place that it cannot be using hexa, then it will basically replace with this pyramid cell. So you have this so-called more towards penta types of 3D elements. Sweep meshing method is sweepable. Any body that's sweepable, assist sweepable bodies, so it will be using it will be you can use this method and basically it will also replace it will basically discretize using hex hex types of mesh. Okay, but in the case of your body, it's not sweepable and you choose sweep, then basically you will fail your mesher will fail. Basically you have to take note on that. Then probably what you can do is you have to find a body that is sweepable using ANSYS. So if you click on your body, then you right click show sweepable body, then it will help you to know where is sweepable that you can apply sweep meshing methods. So in the case of using sweep, so you have to ensure that your body is sweepable. Next is multi-zone. Okay, it's also similar with sweep. Okay, but then multi-zone is more flexible. Instead of sweep, it have to be sweepable. So multi-zone is you can it will, those, let's say it's not sweepable. If mostly it will, if you discretize it, the mesh, it will use a hex type. Okay, if possible, if we all use hex type. So if not possible, then it will use this unstructured mesh basically to fill the whatever that cannot be meshed with unstructured, cannot be meshed with the hex type. Okay, so it's it basically helps us to decompose automatically. Then it won't like it doesn't look like, I mean, the sweep method where it will fail. Okay, if it cannot decompose or under it's not sweepable, then it cannot decompose. So if you want to see this, then probably you can. So if you have a multi-zone, then basically you just have to you no need to like sweepable body. I mean, sweep method it only detect the sweepable body, then it use it discretize this sweepable body using hex. Then this multi-zone, basically you just select the face. Right, in this case maybe 1, 2, 3, and bottom 4 surface. Then basically it will basically discretize using hex. Though the case of is not not available for hex, then it will replaced by other types of so-called unstructured mesh. If the same body you are using sweepable, okay, sweep methods, then you have to slice this body into 4 so-called different components. So like this itself, you have to cut it or slide it into one component. and this one, the bottom part, you have to also slide into the one component. Same with, you have 1 cylinder, 2 cylinder hidden at here, 3 and 4 cylinder all have to be slide off, then only you can apply the sweep methods. So compared to multi-zone, you don't need to do all this slicing or what you call separating the bodies. Okay, so that is one of the difference between multi-zone and sweep. So in the case of sweep method, if your body is not sweepable, then it cannot be completed, your meshing. All right. So again, element mid-side node is like what you have seen. Okay, but then now you will use linear or quadratics. Then under boundary conditions, we have different type of supports that you can relate it to the actual physical behavior. So fixed support is the most common one that we use. So prevent the geometry entity or the phase that we select from moving or deforming. Okay. So frictionless support is basically the phase geometry normal direction to the relative phase. I mean, only the direction is not allowed to move or deforms. Okay, the normal direction relative to the phase that we select. Cylindrical support is more towards prevent the cylindrical phase. You have a cylinder, you have bearings types of so-called support, and basically it prevent that cylindrical surface of phase from moving and deforming. Then under supports, okay, we have to ensure that in the case of you are dealing with deformations, dealing with solid mechanic problems, then we have to ensure that it is constrained correctly. So okay, you know that we have a total of in ANSYS or in our analysis, we have total of 6 rigid body motions. So where you have 3 translations and 3 rotations. So in particular analysis on static, solid mechanic problems. When we deal with static loads, then a lot of time, we still remember we have this KU equals to F. We have to set our boundary. Else, you are fall into this so-called singularity problem or even conditions. So you have to set the boundary in this case. Else, basically to set the boundary, so we ensure that you don't have any rigid body motions, okay, available in your problems, then it can be solved. Okay, so under statics, okay, under solid mechanic problem, we have to set the supports. Okay, in the case of you don't set the boundary, you don't set the support, then basically you will cause this singularity issue in your matrix. Then cannot be solved. So remember to set the support correctly. Okay, then so you can avoid this or you can ignore what we call this rigid body motion, of course, by adding supports. So in the case of no supports, then only applicable for so-called vibration analysis, or here we call it model analysis, where you analyze under free conditions, and we want to know the rigid body motions. In that case, then yes. So in the case of you really want to look into its global deformation, global movement, okay, then the support have to be included, then to eliminate these rigid body motions. Okay, but make sure you don't over constrain it. Okay, so over constraints, then basically you will cause inaccurate results. Basically become too stiff, then the displacement itself, it doesn't reflect the actual conditions. The load, we have many types of loads. Okay, so under solid mechanics, we have force, moment, pressure, bearing load, and so on. External load, we have also inertial loads like acceleration. You can even add the standard Earth gravity, okay, to consider the inertials or the weight of your bodies. rotational velocity. So basically, these are the available loads for us, right, to include in our analysis of solid mechanics problem. For other type of analysis, okay, you have other type of loads like thermal, electric, magnetic loads that can be also involved, but for other type of analysis. Finally, is the context The context is whenever you have assembly, you have more than one component that they are in touch, then NCs will help us to detect the context automatically. So we have few types of contacts. So bonded, okay, if you have two bodies, okay, two components detected, then NC will help us to automatically by default, okay, set the body context to bonded. Okay, so bonded is a default configuration, so is considered as glued together. Okay, so here is no sliding. If you're choosing bonded, then no sliding and separation between these contacted regions of phase allowed. So you are no slide, there is no sliding and no separation. So meaning the surface of these two bonded surface is not allowed to slide as well as separate from each other. Okay, so no separations. That is another type of context that you can choose manually. Okay, if you think bonded is not suitable for the context that you in our analysis, then you can choose other types. Okay, so but usually bonded is good enough. Okay, but in the case of you have a special case, okay, you allow it to slide, okay, but no separations, then you have to choose no separation. So this contact allowed frictionless sliding. So basically, it's allowed to slide frictionless along the contact face, but not allowed to separate. So meaning the face to face cannot be moving separated. So it only can slide. Frictionless contact means the contact model allowed free sliding, no a zero coefficient of friction, and also gap can form in between region in contact. So meaning if you choose frictionless, so you free sliding, at the same time it's allowed a contact to these contact surfaces to be separated. Rough is cannot slide. No sliding can occur because the surface is very rough. Then basically it's an infinite friction coefficient, so no sliding, but it would allow separations. Frictional, basically you have to, if you know the coefficient of frictions of that particular body, then you can set it. Then it allowed to slide. Okay, of course, based on the coefficient of the friction that you have set. Okay, so that is frictional. So most cases, these contact regions basically detected automatically by your software. But we ourselves, we have to judge, we have to evaluate whether this contact is assigned automatically correctly or not. So for example, okay, you have that things that you have to take notes if you are analyzing using NCs. It will help us to define the context. So, but in the case of very thin plate, let's say you are in contact, very thin plates, these two, okay. So of course, the contact surface that is bonded, I would say is this one and the top of the bottom one, right? These two. So that is the reasonable context but because it's too thin, sometimes okay, your NCs will also detect, will help you to what we call assign a contact of your top surface with the top surface of your bottom, or even even the top surface with the bottom of your bottom surface of your bottom plate itself as a bonded contact. Okay, so in that, if that is the case, you have to make sure that you have to remove the bondeds of this and that, right? you have to only ensure you only have a bonded contacts at only these two surfaces. So that is things that you have to take note. Sometimes it is over what we call constraints. So basically later on it basically will affect your accuracies.